Hello students, today we are going to start the new chapter, that is current electricity. In this chapter we are going to study about the flow of current through the conductor. You know that metals are the good conductors. Through the metals, electric current flows. In the 11th standard, you have studied about the good conductors, Ohm's law. The definition of electric current is rate of flow of electric charge through the conductor. Now, current electricity means, here the meaning of the word current is flow, electricity means electric charges. The flow of electric charges through the conductor is nothing but the current electricity. Now, in the 11th standard, you have seen specific resistance, or we call it as resistivity, conductivity, resistance, conductance. According to the Ohm's law, V is equal to IR, and specific resistance rho is equal to RA upon L. Now, here in the 12th standard, according to the new syllabus, we are going to see about the flow of electric current through the conductor. Basically, there are two laws for current electricity. We call them as a Kilchop's law. The two laws are, number one is current law and number two is voltage law. According to the current law, the algebraic summation of the current at any junction in an electric circuit is zero. In an electric circuit, junction means the point at which more than two conductors will meet. And here, branch of the circuit means the conductor between the two junctions is the branch. Now, according to the current law, the first law I have told you that is current law. Current law. The statement of the current law is the algebraic summation of the current at any junction is equal to 0, or summation of I is equal to 0. Now, consider the 5 conductors are meeting at a particular point. We call it as a junction. Let us suppose that this is the current I1, this is current I2, this is the current I3, current I4, and this is current I5. All these 5 conductors are meeting at a point called as junction O. Now here, from the figure, we can say that the current I1, I2, I4 are coming towards the junction, and the current I3 and I5 are going away from the junction. So, according to the Kilchop's current law, the algebraic summation of current at any junction is 0. That means the current which are coming towards the junction are taken as positive, and the current which is going away from the junction are taken as a negative. So therefore, according to the law, incoming current is equal to outgoing current, or sum of the incoming current is equal to sum of the outgoing current. Therefore, I1 plus I2 plus I4 is equal to I3 plus I5. Because the current I1, I2, I4 are coming towards the junction, and the current I3 and I5 are going away from the junction. Therefore, incoming current is equal to outgoing current. Therefore, I1 plus I2 plus I4 minus I3 minus I5 is equal to 0. That means summation of I is equal to 0. So this is what is called as a Kilchop's current law. That is, sum of the current at any junction is equal to 0. It is not possible that all the branches are carrying the current towards the junction, or all the branches are carrying current away from the junction. At least one of the junction should be, one of the conductor should take the current towards or away from the junction, if all other are coming away or towards the junction. Okay, now this is the first law. Symbolically, we can write this Kilchop's current law as summation of I is equal to 0. Okay, now we go to the second law, what we call it as a voltage law. Kilchop's voltage law. Kilchop's voltage law. First one is Kilchop's current law. Now, second one is Kilchop's voltage law. Now, here for the voltage law, here there is a circuit diagram we have to consider like this. Let us suppose that we have taken the three conductors are carrying the current as shown in the figure. So, conductors are having the resistance R1, R2 and R3 as shown in the figure. Now, we call this as A, B, C, D, E and F. The cells are having the EMF E1 and E2. The direction of the current is as shown in the figure. I1, this is I2 and here is I3. Positive, negative, positive, negative. Now the current flowing through the branch AB, that is conductor having the resistance R1 as I1, resistance R2 as I2 and the conductor having the resistance R3 as I3 as shown in the figure. Now what is the statement of the voltage law? The statement of the voltage law is like this. In a closed loop, loop means a closed path. In a closed loop of electric circuit, here A, B, E, F, A, this is a closed loop. Here D, C, B, E, D, here is the closed loop. Or we can take A, B, C, D, E, F, A, this is a closed loop. Here in this circuit there are three closed loops. Now according to the voltage law, in a closed loop of electric circuit, the algebraic summation of product of resistance and current is equal to algebraic summation of the EMF in the loop. Now here if you consider the loop A, B, E, F, A, according to the law, in a closed loop of electric circuit, the algebraic summation of product of resistance and current is equal to algebraic summation of EMF in the loop. Now, if we apply the what is called as voltage law to the loop A, B, E, F, A, B, E, F, A. Then, according to the law, I1 R1 plus I3 R3 is equal to E1. Now, one more thing you have to remember. If the direction of the loop and the direction of the current are same, then take the current as positive. If the direction of the loop and direction of the current are opposite, then take the current as negative. The selection of the loop is depending upon us. You may take the loop as ABEFA or BAFEB. Anticlockwise also you can take. But at that time, here, if the loop direction and current direction are opposite, then take the current as negative. Otherwise, if loop direction and current direction is same, then take the current as positive. So, here, according to the Kilchop's voltage law, I have applied to the loop ABEFA. We have got I1 R1 plus I3 R is equal to E1. Now, what about the EMF E1? If the loop is traced from the positive terminal of the cell to the negative terminal of the cell, then the loop will send the current in the same direction from the positive to negative. Then take the EMF as positive. Otherwise, if you are taking the loop from the negative terminal of the cell towards the positive terminal of the cell, then at that time take the EMF as negative. So therefore, what I have told you, that the direction of the loop and direction of the current sent by the cell is the same, then take the EMF as positive. So this is the first equation we apply to the loop ABEFA. Now we will apply the Kilchop voltage law to the loop CBEDC. Then here CB means we are going from C to B. Current is in the same direction from C to B. Then take it as I2 R2. Then plus. Then BE, same direction, current and loop direction. Therefore take plus I3 R3. And here in the ED there is no resistance. In DC there is no resistance. Then take that is equal to EMF as E2. This is equation number 2. Now apply the Kilchop's current law at the junction B, because B is the junction. Then incoming current is I1 and I2. Outgoing current is I3. Then according to the Kilchop's current law, I1 plus I2, that is incoming current, is equal to outgoing current, what is called as a I3. So this is 3 equation. Okay. Then using the equation 1, 2 and 3, we can find out the current I1, I2 and I3 in each branch of the circuit by knowing the EMF E1 and E2. So therefore, what does the Kilchop's law, voltage law states? In a closed loop of electric circuit, the algebraic summation of product of resistance and current is equal to algebraic summation of EMF in the loop. So voltage law equation is here summation of IR is equal to summation of E. And current law is summation of I is equal to 0. Voltage law is summation of IR is equal to 0. Okay. So this is the Kilchop's current law and voltage law of the chapter current electricity. So this is the voltage law and current law is in the 12th standard. In the 11th standard already you have seen what is the current is Ohm's law, then what is called as the resistivity, conductivity, all that. Okay. Then here this is the first article of this chapter, what we call it as a current electricity. Thank you.